Okay, hi everyone. So I am Matthew Andrews. I'm part of Nokia Bell Labs, like many others of you in the room and on the call. I'm based in New Jersey, and I work with a number of people in the room. This is actually work that we did a few years ago, but I thought it might be. Actually, it was done right before the pandemic, so I haven't had too much chance to publicize it. So I thought I would take the opportunity. Marc Olivier kindly said I should give a talk when I'm here, and so I thought I'd take the opportunity to talk about this particular piece of work. So I'm in the AI research lab at Nokia Bell Labs, and the colleagues that I work with on this project. Sam Borst, many of you know, he was a long-time Bell Labs colleague. He's now at the University of Eindhoven. Two colleagues from Bell Labs in Stuttgart, Siggy Klein and Silvio Mandelli, who did a lot of the algorithm design work and also the simulations. And then Hans Kroner, who's in our wireless business at Nokia, who was really one of the people who was defining a lot of the problems that I'm going to talk about today. So the topic I want to talk about is what happens to wireless scheduling when we want to incorporate slicing dynamics. So let me say a little bit about what that means, and then the key thrust of this particular piece of work is what happens when you adjust scheduling weights in an additive and a multiplicative way. And the reason I wanted to talk about this today is when we started this project, we thought the answers were obvious. And then once we actually started thinking about it, it turned out that a lot of what we assumed to be the answers was not actually the case, and the reality was maybe a little bit more interesting. So I want to give a little bit of an explanation of what facts we were able to discover, but I will mostly focus on the facts. I don't think the proofs are particularly interesting, and they get kind of quite detailed and messy. So let me just focus on just saying what's true. Okay, so arguably when we talked about wireless data, that really became a thing in 3G. I guess the very earliest iPhones had 2G data connections, GPRS connections, but they basically didn't do a whole lot. And so one could argue that only when we got to 3G and 4G was there really such a thing as wireless data connections, cellular data connections. And there was a lot of work in the early days of 3G about how could we provide QoS guarantees to a single user. So essentially, the world we should think about is a base station. So talking to a set of mobile users, and what we wanted to do in the 3G world was to be able to put constraints, say that user in the middle there should get a data rate of more than a megabit per second. And the reason that these type of problems become interesting is in the wireless world, nothing ever stays the same. So you have a channel rate, which is the data rate, the effective rate at which you can transmit to a user, and that's going to change over time. And so if we think of this red and this green user, and this is the data rate that we can transmit to this users over time, then this will be both different for different users. You might have one user close to the center of the cell with a better signal, one on the edge with a worse signal. So it's heterogeneous among users, and it's also heterogeneous over time. And in particular, there might be times when the red user is better, and in general, you want to schedule that user at the times it's good. And there might be other times when the green user is good, and you want to schedule the green user at that time, but you also want some sort of fairness. So that's kind of the name of the game when we are doing wireless scheduling. Now, when it comes to all these generations, what is 5G, what is 6G, arguably this is often more marketing rather than technical definitions. What exactly is the transition between 5G and 6G and 4G and 5G and 5G and 6G? But certainly when people started thinking about 5G, one of the big differentiating features of 5G is that would allow you to provide rate and resource guarantees to a so-called network slice. Now, a network slice was a set of users that would be treated the same. So there's various definitions, there's various applications of network slicing. One version of network slicing is to be able to carve out a piece of the network for a certain type of traffic. So for instance, if you had a network of drones that were talking over 5G, maybe you want to carve out a piece of the network for the set of drones, or maybe a set of robots in a factory. Maybe you'd want to carve out the network for a piece of the network for the robots. Another application of networking slicing is a virtual network operator, so so-called MVNO. You can think of that as a virtual operator that buys a slice of spectrum or buys a slice of capacity from a more traditional network provider and then sells it on to another set of users. So these are the kind of applications of network slicing. But from a technical point of view, what we can think of it is you could have an entity that buys a chunk of the network that you then need to provide network guarantees for. So whereas in the past we might have to only provide network guarantees for a single user, now we have to provide network guarantees for a network slice. So the name of the game with network slicing is we want to provide a negotiated quality of service to a subset of flows. So you can think of this now as a set of users. Again, if these are just phones, then this would be more in the MVNO type of application. But you'd have one set of devices in slice 0, you'd have another set of devices in slice 1. And now instead of saying we want this user to get 1 megabit per second, now what we want to say is all the users in this slice need to be given an aggregate throughput of more than 10 megabits per second. So you can think of this as a mobile virtual network operator that has bought a chunk of bandwidth and wants to ensure that it gets a decent network performance for its users. So just I'll just assume that membership in a slice is binary. There are applications where you could think of this as a real number, but I'll just let alpha ij to be 1 if flow I is in slice j and 0 otherwise. And I'm going to let big R sub I be the long-term throughput to flow I, and I'm going to let big X sub I be the long-term share of cell resources assigned to flow I. So why do I care about these two measures, big R and big X? Well, it's really because, at least when initially people were thinking about network slicing, they really weren't sure about what sort of contracts you would want to give to a network provider. Now, obviously, giving some sort of throughput, that's nice because ultimately that's what users want. They want throughput. However, a number of the operators were a little bit nervous about, okay, do we ever want to provide a set of throughput to users? Because then that depends on where they are. So maybe all we should say is we just want to provide a bounds on the long-term share of the cell resources that are assigned to a particular flow. So we tried to be agnostic to those sort of decisions and basically come up with a solution that can provide constraints both on the long-term throughput to flow I and also on the slice I. This is typos here. This is the flow I. Our constraints will be on the slices. Sorry. So Ri is the long-term throughput to flow I. X sub I is the long-term share of cell resources assigned to flow I. But we want to put constraints on the throughput to slices and the resource share to on the resource share to slices. So basically, what the problem then becomes is we want good throughput to all the users. So we want to maximize the geometric mean of throughput over the entire set of feasible rates. So that's sometimes written as maximizing the geometric mean of throughput, or equivalently maximizing the sum of the logs of the rates. Subject then to slice rate constraints. So we have a lower bound and an upper bound on the aggregate rate provided to a slice, and we also have a lower bound and an upper bound on the aggregate resource share assigned to the slice. And of course, as is always the case when we're talking about wireless scheduling problems, the key thing we have to deal with is the fact that the channel rates are time varying. So we can't a priori decide which time slots are being assigned to a user, which frequencies are being assigned to a user, because the set of channel conditions may change. So let's just put some simplifications and restrictions on the problem. First of all, we'll just assume we've got a single frequency. We're not trying to slice and dice frequencies among the users. Secondly, we're going to assume that within a given time slot, so we'll assume time is slotted, and we're given a time within a single time slot, we can only serve one user. So there's no multi-user MIMO that would allow us. In practice, we can typically transmit to multiple users at a time. Let's ignore that for now. Let's just assume we can serve one user per time slot. And I'm going to denote by Ci sub tau as the channel rate for flow I at time tau. So that basically means for a given user I, if we serve that user at time tau, then this is the rate that that user is going to get. So that will capture the time varying rates. Going to assume that the slices don't overlap. Things become a little more complicated if you've got a given user that belongs to multiple slices, so it will participate in multiple constraints. Another thing that generated a lot of discussion is that, well, ultimately these sort of slice constraints at a single cell are not going to be what's contracted with the slice owner. So if you've got a virtual network operator, then they're going to want to ask for a set of performance guarantees over the entire network. But there's then a question of how does that translate into the per cell slicing constraints? And then there's a whole separate body of work on how can you take wide area throughput and resource share constraints. How would you translate those into constraints at a given cell? Because maybe you want those to depend on the number of users in a slice at the cell at a given time. So in reality, you need a mechanism to convert network-wide service level agreements. So those would be the contracts between the operator and the owner of the slice into per cell slicing constraints. And you both need some sort of economic mechanism to do that translation. You also need some signaling mechanism as well. So that was a separate discussion that I'm not going to get into today. And then lastly, I'm only going to consider slice constraints on rate and resource share. In practice, there's also, especially if you're having a slice that will want to talk to robots with very tight latency constraints, then you might want to put constraints on latency as well. So that's the problem setup. So first of all, just as a little bit of a review, I suspect this is common knowledge to many of you. Well, what's the baseline scheduler for scheduling to wireless users in a time varying network? It's the so-called proportional fair scheduler. So what this does is, so for every user, they have their channel rate at time tau, and you have this, and then you have this long-term average throughput to the user. And what proportional fair will do is it will always serve the user that maximizes the instantaneous channel rate over the long-term average rate that user has got. So what that does is it allows us to generally serve users that are in a good position, that they've got a good CI, but we want to get some sort of fairness. So if a user has not been served much in the past, then its rate R sub I will go down, and then we're more likely to serve it. So that will achieve the fairness. So how do we measure the rate big I? Well, this is just an exponentially averaged measure of the throughput to user I. So at any time tau, we let S sub I of tau be the rate that the user gets, which basically means he gets rate C sub I of tau if flow I is served and 0 otherwise, and then we just use that to update our estimate. I should also mention another simplification here is that we're assuming full buffer traffic, that all users always have data to serve. Of course, again, if you have latency sensitive traffic, typically many users will have an empty buffer at a given time, and that complicates things a little bit, but let's not get into that now. So what's known about proportional fare? Again, very widely known. If you look at the rate region that's achievable for the set of users, then a proportional fare will maximize the geometric mean of the rates over the achievable rate region. So this rate region is due to the time varying nature of the channel is typically not linear. So you typically get this convex rate region of the set of rates that can be achieved, and proportional fare is known to maximize the geometric mean of throughput. And the other property, under some conditions I won't go into, but under fairly natural assumptions, the resources are shared fairly. So what that means is that the resources provided to each user are the same for all users in the network. And the way to think of this intuitively, so if you think of all user channels as being some sort of channel mean and then having the same fluctuations, then once you, if you look at the definition of proportional fare, you can basically think of the channel mean sort of cancels out top and bottom. And so basically, you're always serving a user which has a good rate relative to its average, which essentially means that typically speaking, all users will be getting the same share. But this is not the same as just saying we're just going to give every nth time slot to each user, because we're still generally trying to pick users when they're in a good position relative to their average channel rate. Just as an aside here, sometimes what one wants to do is do so-called weighted proportional fare, which is you actually want to give a boost to some users and basically maybe double the rate to a particular user, maybe if they paid more and these sorts of things. So sometimes people talk about weighted proportional fare scheduling. So in the weighted proportional fare, each user will have a weight W sub I. And what we want to do at any given time slot is serve the user that maximizes W I Ci tau over big Ri. And what this is known to do is basically maximize the weighted sum log rate. And also, if the channel rates are constant, so if they actually don't vary over time, then the resources are then shared in proportion to these weights. So basically, instead of each user getting a 1/n share of the rate, the resources are shared in proportion to W sub I. Just as an aside, I'd just like to mention that for time varying channels, this proportionality does not hold in general. So it's something that I've found that many people assume because people know the result for proportional fare, and they kind of know intuitively what would happen in the case of constant channel rates. But for weighted proportional fare, that does not hold in general. So just to give a quick example of this, so suppose we have two users with weights W0 W0 W1 a 2 1, and if we have a if we have each user having channel rate 1 with probability 9/10 and channel rate 10 with probability 1/10, then you actually get some quite complicated assignments to the different channels, and ultimately you get a ratio of resource shares that are not equal to the ratio of the weights. So let's go back to the main problem, which is how to meet slice constraints. So let's suppose we want to maximize the geometric mean of throughput subject to these constraints on slice throughput. So we basically want to, you can think of this constraint as maximize it as we want the aggregate rate for the slice to lie between this lower bound and this upper bound. So how can we do this? Before I just mentioned that, I think one obvious question is, why would we even want to have an upper bound on rate constraints to a slice? I mean, there are obvious reasons for a lower bound. You want the slice to get certain performance. Why would you put an upper bound? Generally, operators do ask for this because it allows them to do differentiation between users. Maybe you want to sell a portion of your network for not much money, but maybe then you want to basically put a cap on the resources that that particular slice would get. So the general mechanism we're going to use for this type of solution is just a simple token bucket type of mechanism, whereby you're putting some tokens into your bucket. So you have your token level Q sub j, and maybe the easiest thing to talk about first is how do we take tokens out of the bucket? We basically take tokens out at the rate at which data is being served. So this is the rate at which user I is served at time tau. So that's Si sub tau. So this sum here is the rate at which slice j is being served at time tau. So at any given time, we take those rates out of the bucket, and then what we do is we fill in this bucket at rate either at the lower bound or at the upper bound. And generally, if this token level is above 0, it basically means that we're up against the lower bound, and we should be feeding tokens at the rate of the lower bound. If the token level goes below 0, then it basically means we're up against the constraint that's the upper bound, and then we should put in tokens at that rate. And generally, if we're hovering around 0, then that means we're kind of in between the constraints, and so we don't have things. So then we're neither constraint is biting. But if we're consistently above, then we're at the lower bound. If we're consistently below, then we're at the upper bound. So this is how we'll satisfy the constraints. Yep, question.
So if you predefine the betas, why should there be a solution to the problem? If you ask too much in terms of rate for every slice, physically maybe that, I don't know, SMR noise is high for some whatever reason, so these guys are far away and you can't make it. So I don't understand why this should be feasible.
Exactly, and it may not be feasible, and then and then we get into the whole problem of admission control or overload control, and how do you give yourself a feasible problem. So then there becomes a whole, and thank you for the question, because then there's a whole question of what do you do if things are unfeasible? I mean, do you either just say we're not going to accept any more users for this slice into the network, or do you say, okay, I'm just not going to satisfy this constraint anymore? That's a whole separate question. Let's for now assume it's feasible, but that needs to be dealt with in practice as well. And then we can do the same mechanism as well for the slice resource constraint. So if we want to say that the resource constraints are between an upper and a lower bound, then we can have a similar token bucket mechanism that really keeps track of how many resources are being assigned to a particular slice. So what we would typically do is we'd have a set of slice constraints. We have multiple slices in the network, some rate constraints for each slice, rate resource constraints for each slice, and then we track those with these token bucket mechanisms. And so then just going back, this is just a repeat of what the problem definition is. We want to maximize the geometric mean of the throughput subject to both the slice constraints and the resource constraints. And again, we're assuming this is feasible, but that of course may not be the case. So when we originally started looking at this problem, we looked at an algorithm that we call scheduling metrics for slicing, and we looked in an additive form of this. So this was in an early part of the work. And so what does the additive solution look like? So basically, it just takes these token buckets and adds them as a penalty term to the scheduling metric. So we start off with plain proportional fare. We want to serve a user that maximizes the standard proportional fare metric, but we then want to add on to it the penalty terms according to the slice and the slice rate and the slice resource levels. So generally, there'll be some constant factor delta that just allows us to balance whatever units we're using for the token buckets with whatever this ratio is going to come out of be. And in general, playing around with this delta sort of tells you how responsive you're going to be. You know, it basically affects the time scale over which you're satisfying these constraints. So we basically have this token bucket that is going to be associated with the slice rate constraint, and then we have a token bucket that's associated with the slice resource constraint, and we add them on additively. But because the difference between the rate constraint and the resource constraint is we actually put the channel rate with the rate constraint penalty term. So this turns out to be the what we're able to this turns out to be the scheduling metric that we'll use in order to satisfy the slice constraints and the both the slice rate constraints and the slice resource constraints. And again, not going to get into proving why this works, but you know, you can think of these as Lagrange multipliers for the constraints, and then it's maybe not too implausible to believe that this type of this additive term will allow you to satisfy the metric associated with the proportional fare term subject to the constraints that are associated with these penalty terms. And as I say, I'm not going to go into the proof, but if you want to do the proof, it gets quite messy because you've got to kind of get rid of the dynamic channels. So you've got to kind of look over time scales and take fluid limits and do all sorts of those things. So as I say, I'm not going to get into that today. The other thing I'd maybe say about these type of penalties is earlier on, when people started looking at these sort of constrained scheduling problems over time varying channels, there was a body of work that looked about trying to adapt the denominator of the proportional fare metric in order to basically penalize users that are or slices that are not within the constraint. But having these additive Lagrange multipliers turned out to be a more stable way to achieve this. So, so in some sense, this is the starting point for how you can achieve these slice constraints. So let's just look at a very toy example. So let's just assume we have constant channels, whether we have 6 users with channel rates 1, 2, 3, 4, 5, 6. These stay constant over time. And let's suppose we have 2 slices, one with a rate constraint only, no resource constraint, and 3 users, and then a slice 2 with 2 users and a resource constraint only and no rate constraint. So let's put these constraints, and then we say we want to optimize the geometric mean of the throughput, which is equivalent to just the products of the rates. And it turns out that when we do the optimization, we get a token bucket for the slice 1 rate constraint to have this value, a token bucket for the slice 2 resource constraint to have this value, and then you get a set of rates, and you get a set of resource shares for all the users. But one thing to note here, and this was one thing that caused some unhappiness with the people who are looking to implement this type of solution, is that within a slice, we've now got resource unfairness. That if we just do this optimization problem and we want to optimize this, this objective subject to this constraint, in order to maximize this, we're no longer treating the users within a slice fairly. So again, remember that for plain proportional fair, if you just want to, across all users, maximize the geometric mean of throughput without any constraints, then the rate to each user will be the same. But now once you start putting these resource constraints and rate constraints on, then maybe you'll be driven to an operating point where you no longer have that fairness. And so there was a belief, I don't know whether this is true or not, that some operators may get unhappy if by having a solution like this, they start to see very different performance to users in a slice. You know, the proportional fair, you know, the fact that each user gets the same resources is kind of a nice property. And so maybe you want to continue to enforce that. So then we started to look at another constraint that we call intra-slice resource fairness, which basically says that if 2 flows belong to the same slice, we want the resources allocated to that slice to be the same. And the additive nature of this algorithm we put here basically prevents that resource fairness from happening. Generally, if you put a multiplicative weight on this term, then if all the users in the slice have the same multiplicative weight, then so if this is not here, we just have a multiplicative weight, then you would maintain the fairness. But once things become additive, then you no longer get this fairness within a particular slice. But as I say, there was a thought that some operators may want to have that property because it kind of reminds us of proportional fair. So maybe we want to impose it anyway. So then the problem that we started to think about was, well, what happens if we want to now do the following problem? We want to maximize the proportional fair metric, subject to constraints on the slice rates, subject to constraints on the slice resources, and then subject to intra-slice resource fairness. So we want the flow rates to be the same if they belong to the same slice. So then what are we going to do? So then we started, because as I was saying, if you put multiplicative weights on the proportional fair metric, then in some sense you get that for free. That if you have 2 users that are in the same slice, the way we think about multiplicative weights is that we again have our resource constraints here. We would have our rate constraints here, have a token bucket for our resource constraints here, and we would put these into basically an exponent, so we have a constant to this exponent. And I think I'm missing a C the rate constraints that we had on the additive terms before, which is basically saying we take the additive Lagrange multipliers that we had before, and we basically put them in the exponent and create a multiplicative weight that way. Now it turns out that when we just had the single user rate constraint problem, so you remember at the beginning of the talk I said in the 3G and 4G world, all our constraints were for single users. In the single user world, it's actually possible, and I won't go through the derivation, it's actually possible to take this additive form and basically do some algebra, and you can actually start treating the weights as multiplicative weights. You can get equivalent optimization problems. And so there's really no difference between thinking of additive penalties and multiplicative penalties. And so this will give you exactly the same constraints and performance as you got with the additive term. And originally we thought that this was going to apply for the slice constraints problem as well, until we thought a little bit harder, and then it turned out that that was not going to be the case. So in terms of what are the properties we get by looking at these additive penalties and the multiplicative penalties, then what are the basic facts that we get? So first of all, let's just think about the case where we don't have time varying channels. So our channels are just constant over time. So what we're able to prove is that the version of the algorithm with the additive penalties, it does what we want. It optimizes geometric mean throughput subject to slice rate and resource constraints. However, as said before, we don't get this intra-slice resource fairness. So we may get fairness with unfairness within a slice. So for these, for the case of, so what do we get if we impose the multiplicative weights? So in the case of constant channels, then what we're able to show is that these multiplicative version, it optimizes the proportional fair metric, the geometric mean throughput, subject to our rate and resource constraints, and subject to the intra-slice resource fairness constraint. However, because this is an extra constraint, this will potentially lower your objective. So you have to think about how much do you care about this extra constraint, and also in terms of infeasibility, imposing this fairness may turn a feasible scenario into an infeasible one. It may be the case that you can only satisfy a set of constraints by not giving this fairness within a slice. So maybe these are fairly natural things. And then the other result we're able to prove is that suppose you only have resource constraints, and certainly some operators, prefer to think about resource constraints only because, maybe it's hard to provide guarantees on rates. So suppose we have constant rate channels, and suppose we only have resource constraints. So in that case, we're able to show that both the additive and the multiplicative versions of the algorithm optimize your geometric mean throughput subject to these resource constraints and subject to the intra-slice resource fairness. And what are we able to show? So, these are the simplest things to think about if we've got constant channel rates only. But of course, generally, in the world of wireless, you have to worry about variable channels. So in that, the situation became somewhat murkier, and we're only able to get some partial results here. So I think characterizing the full situation of variable channels, I think is still a very nice, interesting open problem. So suppose our channel rates vary. What we were able to show was similar, but not quite as clean. So first of all, the additive version of the algorithm is what optimized the geometric mean throughput, the proportional fair metric, subject to our slice rate and resource constraints, but doesn't satisfy this intra-slice fairness. So that's what we mentioned before. The multiplicative version, where we have multiplicative penalties on our scheduling metric, achieves the intra-slice resource fairness. So because everything is multiplicative, then we have fairness between flows within a slice. But this result before about what happens if we have resource constraints only, we don't even have the multiplicative version may not satisfy proportional fairness subject to resource constraints only. And in fact, in pathological cases, the optimal solution may not have rates that are on the boundary of the rate region. So, sorry, maybe went back too far. So typically with most of these wireless scheduling problems, you have a rate region like that. These are the set of feasible rates. And typically, any optimal point will be on the boundary of this rate region. What we found with the case of variable channels is that when we do this type of optimization here to try and get the intra-slice resource fairness, we may have difficulty getting this multiplicative algorithm may not optimize the metric subject to the resource constraints only, because the optimal solution may require non-Pareto optimal rates, and these type of simple greedy algorithms are always going to put you at a point on the boundary. So if your optimal point is not on the boundary, then it's not going to get you there. So I don't really want to go into the details of this, but just have a concrete example. This was a case where most of the time these are our channel rates. Every so often we get these very big channel rates, and just plain proportional fair will assign type A slots to flow 1 and all type B slots to flow 2, and so we get these rates. So this is the standard proportional fair giving the same resource share to all users. However, if we put a min resource share for flow 1, so this is the single user slice, if we ask, say this is going to have this constraint of we want this particular fraction of the resources to go to flow 1, then this is the optimal solution. A certain fraction of type A slots and a certain fraction of type B slots go to flow 1. And this gives you a set of rates which turn out to not be on the boundary of the rate region. So I don't particularly want to worry about the details too much. Just want to say that you get some really pathological cases where when you're trying to have all these constraints, you may not even get to the boundary of the rate region. The optimal point may not be there. Okay, so yeah, question.
Does it make sense to say that in this kind of pathological cases, the problem is kind of reposed, because many way, no one will want a non-Pareto optimal.
Yeah, I mean, you could argue that maybe this is still an algorithm and it will ultimately get you what you want, even if it's not the solution to the formal problem. But and you can see, intuitively you can see why it's a problem, right? That resource constraints somehow are contradictory with rate constraints and doing rate. So somehow when you're trying to optimize rate subject to resource constraints, you get these things fighting against each other. We have a simulation scenario. Let's not go through all the details of the simulation scenario, other than to say we have two slices, one slice with 6 users, one slice with 8 users, and we're going to put some constraints on the first slice. The first thing we're just going to look at is what happens if we have target. If we have a target aggregate rate for the first slice, and then what we want to do is when we use these algorithms, then what's the geometric mean of throughput we're going to get subject to these target slice rate? I think the the title says min rate constraint. There's actually a target rate constraint where we both want the min and the max rate to the slice to be exactly the same. So what we get is this hump-shaped curve, because as the target slice rate for the first slice is low, then that will constrain what we can give to the whole network. But ultimately we get to an optimum point, but then we drag it further, then that constrains the solution too much. And so the geometric mean throughput goes down. And so this basically illustrates the story we said before, that with these additive penalties, we actually get better geometric mean of throughput, but we lose this intra-user slice rate, intra-user fairness between the users. This is basically if we've got the rate target to be two cases, one 6 and the other 15 in megabits per second. This basically is showing that both algorithms are essentially achieving these rate constraints. When it's low, do it pretty cleanly. When we do it when it's high, then at least for some of the drops, we don't quite get there, but then that's where we're close to infeasibility. So this is basically showing that the slice rate constraints are achieved. This is also to illustrate the difference between additive penalties and the additive terms and the scheduler metric and the multiplicative terms, is that this is showing what for a given target slice rate, then what are the rates that are achieved in the solid curve, and then what's the resource share between the slices in the dotted line. So basically, as the target slice rate goes up and the achieved rate goes up linearly, showing that we're achieving this rate until we get to infeasibility. And first of all, this is to show that the multiplicative version of the algorithm hits infeasibility first, that kind of becomes sublinear earlier, which basically shows that the additive version of the algorithm, because it's not giving this intra-user resource allocation, intra-user fairness, so it's able to achieve the rate for longer. And then secondly, if we look at the rate, the resources assigned to the slice with the constraint on it, then that goes up pretty much linearly with respect to the multiplicative algorithm. But for the additive algorithm, when the slice rate gets very high, this then becomes sublinear, because it's achieving the rate by playing games, by essentially within the slice, it's giving a lot more resources to the good users within that slice. So again, that's really an illustration that it's achieving these high rates by essentially providing unfairness within the slice. And lastly, here's a metric that's meant to capture fairness, basically saying what's the difference between the resources assigned to users within a slice versus the resources they would get if we were completely fair within a slice. And this is to show that the multiplicative algorithm gives you essentially gives you fairness, and the additive algorithm doesn't provide fairness. So I think I'm at the end of time. I was told to keep to around 50 minutes. So just some conclusions, in that complex slight rate and resource constraints can be supported in the wireless scheduler via simple token-based extensions to proportional fair. Whether you want to use additive penalties or multiplicative penalties really depends on whether you believe that being fair to users within your slice is important. So maybe for a virtual operator, that would be important. And I think maybe, at least in my mind, the most interesting thing about this is that, at least from when we started the problem, we had various algorithms that worked for single user constraints. And originally we thought that going to multi-user constraints would be exactly the same, but it actually turned out that the problem became significantly richer, and you got more pathological cases once you have to deal with these aggregate rate and resource constraints. So that concludes what I have to say today. Thank you very much.
Thank you, Matthew. So, any question in the room or on the bridge?
Mm-hmm.
I come back to my earlier question. And so, I mean, you said you would not like to enter the proofs, but so does this additive or multiplicative algorithm can prove that when it applies, when it is used, you get something which is what you want, and which maximizes this product of rate, for instance, over the classes.
Mm-hmm.
That first question. And second question, if it is infeasible under the constraint, what happens to the algorithm?
Okay, so the second question is maybe the easier one to answer. So so in a way, the algorithm actually gives you. What's the thing with these buckets? So in a way, actually, the algorithm gives you a very simple admission control method in the sense that when things are infeasible, these token buckets start blowing up. And so one of the most natural things to do is to start taking the constraints away for those users. You'll basically say, for a given slice, if it blows up, you either stop serving it completely, you don't allow it in the network, or you just say, okay, I'm no longer going to provide constraints for that. And I think that's probably the cleanest way to do it, is you just start looking. So again, that's a whole separate talk of how you want to deal with these things. But there's very natural things you do. It blows up, you then get rid of it, and then maybe sometime later you start to see, well, can I start imposing this constraint again? And then you do it. So I think it's hard to really make very clean statements about what such algorithms do, but I think it's a very natural heuristic that if things blow up, then you do that. And then all the statements are basically, what the proofs say is that if you run this algorithm, and typically the easiest statement to prove is if you run this algorithm and it converges, then it will converge to the optimal solution. Once you have these constraints, proving convergence is actually not always feasible, or at least I don't know of the proof. So we have proofs for pure proportional fair, right, that it will always converge to the optimal point. Typically, this statement, what you're able to do with the fluid limits is say that if it converges, then it must converge to an optimal point. So that's typically where we get to for these type of things.
There's no certitude of convergence.
But there's no certitude of convergence.
If it doesn't converge, perhaps another algorithm will converge, but
yeah.
the solution.
Yeah. I mean, I don't think we know of. I don't think I know of any examples where these things don't converge. But I think it's really the convergence proofs that work for proportional fair. I don't believe they necessarily work for this. The ones I know of.
When it doesn't converge, what happens? It sort of oscillates, or.
Well, as I say, I don't know of examples where it doesn't converge. It's just we don't have the proofs of convergence. But I don't actually know of an example where it wouldn't work. But yeah, I think that's actually an interesting question. Any questions on the bridge?
No, thank you.
Yeah.
So,
Okay,
thank
one
you
more
again.
question.
Yes, one more question. So,
Yes, sir.
So here it's the single base station, but what happens in a network? So the decisions that you take at a given base station through whatever mechanism might influence what happens in another cell, right? So does the problem have any extension to the cellular architecture beyond the one base station case in the W?
Yeah, I mean, obviously you could you could formulate some problems with taking into account interference and things like that. I mean, my experience is nobody in practice wants to worry about these things, in sense that the CSI information is essentially given to you as an input for this cell. So that takes into account the interference from the other cells. trying to actually manage that by having a multi-cell scheduler, I don't think any practical schedulers are trying to do that yet, as far as I know. So I think this is the practical problem that people are worried about. But of course, you could formulate, in an ad hoc network context or those sorts of things, you could formulate the multi-cell problem for sure. And then I guess you can do, probably do the standard things that you can do for, for general wireless network scheduling, right? Instead of, a single cell, you want to pick a single user, you want to pick the aggregate, you've got a set of available scheduling decisions, you want to pick the aggregate scheduling decision that maximizes this sort of metric. So I'm assuming it all kind of goes through, but we didn't think about it that carefully. But
I think might be very different because it might be good to schedule nobody in a given cell, which people do in a set of
right,
processes,
sure.
If interference is very high.
Yeah.
So
but I think if you have pure centralized scheduling, that might be, that might just come from, I guess it's all about taking the aggregate, the long-term problem and turning it into what do you want to do in this time slot, right? And so it may be that, based on the interference, then that's the decision you want to take at that given time. So
what you say, you could frame the multi-cell problem in the times.
Yeah, I think, as people did with, the ad hoc proportional fair, I'm guessing those sorts of things would still go through.
But then there's question that so you said that one of the assumptions was that certain times out only one user should be scheduled.
Yeah.
If you have multi-cell, you still have to take into account that.
Yeah, but I mean, I think all of those things are just for simplicity, right? I mean, the general problem is you have a set of feasible scheduling decisions at any given time, and that could capture multi-cell with interference. It could capture multi-user MIMO, all those sorts of things. And then what you want to do is, instead of having like an argmax I, it just makes the things easier to write. You would just say, I want to pick my scheduling decision from the set of feasible scheduling decisions that would maximize this sort of aggregate metric across all users or across the network. So I think it's probably just messier to write rather than it's fundamentally a more complicated problem. Yeah.
Your assumption of full buffers. What happens if one slice you cannot really rely on things being operating at full buffer? Like you have a IoT slice versus another slice which has full buffers, like normal traffic. Do you have any feeling for?
Yeah. So I mean, I think for that is, anytime you've got empty buffers, you kind of ignore the constraint, right? You don't even keep track of, you kind of freeze the buffer. I mean, I think that's the simplest heuristic. If you've got no traffic, you just keep the buffer frozen, and then that. I mean, you still maybe get into issues where if you've got a slice with 100 users and only one of them has any traffic, do you want to give like a massive amount of, maybe you want to, relax the slice constraint if you've only got like 1% of the users in the slice actually have traffic. But I think again, you get into the realm of heuristics rather than